Hi, and welcome back to my videos for General Chemistry 1. In this video, we'll start learning how we can put atoms together to form molecules, and what the structures of those molecules are. We'll find out that it's yet another skill that the periodic table can help with. In fact, we'll see that the periodic table gives us essential information we'll need in order to form molecules that are realistic. To begin, let's remember something we learned about back in video 22, condensed electron configurations. You might remember that the periodic table has its shape because it reflects the orbitals of the valence electrons in each element. For example, from the periodic table, sulfur has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p4. We also said that we can abbreviate this by substituting the first part of this by the chemical symbol of the last inert gas before the element we're looking at. So, in this case, the last inert gas before sulfur is neon, so we can substitute everything up to 2p6 with the symbol for neon in brackets. The reason this is important for today's lesson is that writing the configuration this way usually splits the electrons into two groups, the core electrons and the valence electrons. I've mentioned before that it's the valence electrons that do most of the interesting stuff in chemical reactions, and today we'll see that they also do all the interesting stuff when atoms combine to form molecules. So, sulfur has 6 valence electrons, 2 from the 3s orbital and 4 from the 3p orbital. On the other hand, molybdenum has a condensed electron configuration beginning with krypton and then 5s2, 4d4. That means it too has 6 valence electrons total. It turns out that we can tell how many valence electrons an atom has just by looking at the periodic table. This is very useful information when we want to draw the structure of a molecule, which is what we'll begin learning to do in this video. It turns out we can draw the valence electrons of an atom using what's called a Lewis dot structure. To do that, all we do is draw the symbol of the element and then draw the valence electrons as dots around it, on the top, bottom, left, and right. There are just a few simple rules for the dots. First, remember, an orbital can only have up to 2 electrons in it, so each side of the element can only have up to 2 dots. Second, remember that Hund's rule tells us that each orbital in a set should get 1 electron before the electrons start to pair up. That means each side of our Lewis dot structure should get an electron before we start to pair them up. So, for example, the Lewis structures of the second row of the periodic table look like this. The dots go 1 per side until each of the 4 sides of the element have a dot, and only then do we start pairing them. The third rule is that it doesn't matter which side of the element you put dots on first. So, for example, the symbol for magnesium has 2 dots, and these can go on any 2 sides of the element. All of these symbols are correct. The same is true when you start to pair the dots. So, all 3 of these symbols would be correct for sulfur. Finally, there's one more rule, although we're allowed to break this one sometimes. You'll notice that some elements have lots of valence electrons. For example, gold has 11 and gadolinium has 10. That means a Lewis structure of those elements would have lots of dots, and it could be very hard to squeeze them into the symbol. For that reason, we usually don't draw Lewis structures for atoms in the transition metals or in the F block of elements. Instead, almost all Lewis structures we draw are just for the atoms in the S block or the P block. Lewis dot structures are named for the person who invented them, Gilbert Lewis. Lewis made many important discoveries in chemistry, including discovering some of the most important properties of acids and bases, which you'll learn about in general chemistry too. He was also the mentor of a lot of other chemists who went on to win Nobel Prizes, including Glenn Seaborg, who even has an element named after him. But despite all of the great work he did, Lewis himself didn't receive a Nobel Prize, although he was nominated for it an amazing 41 times. Anyway, Lewis dot structures are very useful to chemists for many reasons. For example, they can help us understand some of the differences between ionic and covalent bonds. Imagine we have a molecule of sodium chloride. Sodium has 1 valence electron, and chlorine has 7, so their Lewis structures look like this. When you join them to form a molecule, the 2 unpaired electrons pair up, and that's the bond that connects them together. In the last video, we talked about electronegativity, and if you look at the electronegativities of sodium and chlorine, you find that they're 0.869 for sodium and 2.869 for chlorine, for a difference of 2.000. As you might remember from that video, this makes the bond between them an ionic bond. And since the chlorine is so much more electronegative than the sodium, the electrons in the bond reside mostly on the chlorine. But look what that means for the Lewis structure. Since the 2 electrons in the bond are mostly on the chlorine, it means that the chlorine is surrounded by all 8 valence electrons, and the sodium has none. It's transferred its valence electrons to the chlorine. In an ionic bond, that's always true. One of the atoms transfers electrons to the other. This is an example of an important idea in chemistry called the Octet Rule. The Octet Rule says that atoms are most stable when they have valence shells that are either completely full or completely empty. For elements in the S and P blocks of the periodic table, a full valence shell would have 8 valence electrons, so that the electron configuration would end with S2p6. That's why it's called the Octet Rule. For transition metals, a full valence shell would end with S2d10 for a total of 12 electrons. But as I said, we don't usually draw Lewis structures for transition metals. The Octet Rule helps to explain why some ions have the charges they do. For example, ions of elements in this column usually have a charge of -1. That's because those atoms have 7 valence electrons, so adding 1 gives them a full valence shell, which makes them more stable. Meanwhile, atoms closer to the left side of the periodic table tend to lose electrons so that they have empty valence shells. For example, aluminum usually loses 3 electrons to become an aluminum plus 3 ion. So elements with over 4 electrons in their valence shell usually gain electrons until they obey the Octet Rule, and elements with fewer than 4 electrons usually lose them until the valence shell is empty. There are lots of exceptions to the Octet Rule, and you'll see some of them in the homework problems. The most important exception is hydrogen. Hydrogen has an electron configuration of 1s1, and there is no such thing as a 1p orbital, so a full valence shell for hydrogen only has 2 electrons, not 8. Also, since hydrogen only has 1 orbital, a hydrogen that gains a second electron will have it pair up with the first one immediately. The Octet Rule is also useful when we're trying to understand what molecules look like. For example, suppose we have a molecule of magnesium chloride. From the periodic table, we know that magnesium has 2 valence electrons and chlorine has 7, so their Lewis structures look like this. When we connect them, we can see that the chlorines both gain an electron so that they get a full valence shell, and magnesium loses its electrons so that its valence shell is empty. The same is true for potassium nitride. In this molecule, the potassiums have 1 valence electron and the nitrogen has 5. The Lewis structure shows that the potassiums each lose their electrons and the nitrogen gains them so that it has a full valence shell. But notice all the examples we've looked at so far have been for molecules that have only ionic bonds. The situation's different for covalent bonds. As we saw in the previous video, the difference in electronegativity between the 2 atoms in a covalent bond isn't as large as in an ionic bond, so electrons aren't transferred from one atom to the other. Instead, in a covalent bond, the electrons are shared by the 2 atoms. For example, imagine a molecule of phosphorus trichloride. Phosphorus has 5 valence electrons, and chlorine has 7, so their Lewis structures are these. When we combine them to form a molecule, we get this. This time, the bonds are all covalent bonds, so the electrons are shared by both atoms. That means the chlorines each have 8 electrons in their valence shells, and so does the phosphorus. This is also true for a molecule of ammonia, which has the formula NH3. Once again, the difference in electronegativity is too small to make these ionic bonds, so instead the electrons are in covalent bonds, and they're shared. Notice that the nitrogen has a full valence shell with 8 electrons, and the hydrogens have full valence shells too. Remember, hydrogen is an important exception to the octet rule, so a full valence shell for it contains only 2 electrons, not 8. Well, that's all for today. Now that you know about Lewis structures, we're ready to find the structures of larger and more complicated molecules, and that's what we'll start to do in the next video. So until next time, have a good week.